Now I will just give you all an interpretation of Kepler's second law. I will not state it. I will not state it. It is given in your textbooks. So okay, let me consider the elliptical orbit again. Or let me take an ellipse. And if this is a foci. Okay. Now the sun is here. Example at the foci. And the planet Earth is here. At a time, consider it as t1, some time. And if the planet moves in this direction, and if it reaches here, at a time consider t2. Then consider this area ABC. Now again, consider if the planet Earth was here somewhere, at a time somewhere around t3. And if it reaches here, at a time consider t4. Now this what I have drawn is not exactly correct geometrically, but I'm just giving you all an interpretation. So if modulus, now what is a modulus? Modulus always gives me positive value. So if example t2 time t2 minus t1, if it is equal to t4 minus t3, then okay, this area DE, okay, then area ADE is equals to area ABC. So these two areas are equal. Now what I mean, example, just take a simple example. Please keep in mind that what I'm taking is not up to scale. I'm just giving simple examples. Example, if the time was 10 o'clock something, okay, and if you reach here at 11:30. Similarly, time 3 it was 1 o'clock, and if you reach here at 2:30, okay, so what will be, how much difference you will get? 11:30 minus 10, you will get 1.5 hours, okay. Similarly, 2:30 minus 1, you will get something 1.5 hours. So if the timing is the same, then the area swept are also equal. That is Kepler's second law. Now Kepler's third law is very trivial and it's very simple. The square of the period of revolution. So okay, what is period first? It is a time taken. I'm not writing everything, but time taken to complete one revolution. The time taken to complete one revolution is called a period. Means to move in a completely entire elliptical orbit and to come back to the same position is called one revolution. So if you see, the time period will be 365 days in a normal year and 366 days in a leap year. Actually it is 365 days and 6 hours. So why to take 6 hours? So in 4 years we consider 6 plus 6 plus 6 plus 6, that is 24 hours, and we consider it as 366 days once in 4 years. That is called a leap year. Okay. So the square of that much time, I will represent it as t. It is proportional. The square is proportional to the cube of the mean distance of the planet from the sun. Now why this is happening? Take the rough figure. Sun is here and the planet Earth is here. Okay, then the Earth will come here, then the Earth will be here. After some time Earth will be here. Distance is changing because the focus is not at the center, so this distance will be r1, r2, r3, r4 and so on. There are many distances, you can draw infinite lines. So mean is what? If there are n observations, then the mean is, in this case it will be r1 plus r2 plus dot dot dot. That means there are many more, r3, r4, r5. There are many, you can draw so many. Rn upon the total, that is n, because there are n observations. Example, the mean of 5 and 3 is 5 plus 3 upon how many observations are there? 2 is equals to 4. So that is why the term comes cube of the mean. So your r will be r1 plus r2 plus dot 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 rn up till n. This is Kepler's third law. And since t square is equals to proportional to r cube, when I remove the proportionality, I will get something k r cube. Proportionality is removed. So t square upon r cube, if I take division here, it will be k, some constant. This is Kepler's third law.